Okay, so this video is going to be on Gauss's law and how it works in the spherical symmetry. Um, First of all, let's go ahead and put down a point charge. Now, a point charge is just at a single point, and so that there would be very strange if the field was somehow different on the right versus the left. We're going to expect the same field strength 1 meter to the right and 1 meter to the left, or above or below, or any direction. And so it's no wonder that the field is the same in all directions. And so here's a little mobile picture of a point charge. I like to call this the curtain test for spherical symmetry. And so the curtain test, what I mean by that is that if you cover up the picture and I do something to it, and I'm going to do something to it, and I'm not going to tell you what, and I show it to you, you can't tell that I did anything. What I did was I rotated this, and of course, if I rotate it and I change the top to the bottom, well, a point charge is still a point charge, and so since the point charge itself looks the same, why would the field, could I tell from the field that it changed? And of course you can't. No matter what I do to this thing, if I rotate it like this, or like this, or like this, you can of course tell. And the reason is that because the charge itself hasn't changed, then I shouldn't be able to tell that I did anything from the field itself. Okay, so if upon some sort of rotation or manipulation, you can't tell from the charge itself that there's been any change, that any change occurred, you can't tell by looking at the field either. Okay, so that may not be so clear here from the point charge, but let me give you another example. So I'm going to show you another charge configuration that we're familiar with. And so here's your plus minus charge. And I'm going to cover that up, put the curtain, so to speak, so you can't see what I'm doing. I'm going to do something to it. Oh, and I guess I should point out a few features of it. So right now the positive charge is on the left, negative charge is on the right. And so the field is generally kind of has a rightward point. So let me rotate it now, or maybe not, I don't know. So let's do the curtain test. So if I take a look here, I'm covering up the two charges, but even just looking from the field, I can tell something has changed. Now the field lines are pointing to the left, and I can tell that there was some manipulation that occurred. And of course, what I did was I rotated this so the plus was on the other side, the minus was on the other side. And so I didn't need to see the charges. I could tell just by looking from the field, there's a left-right asymmetry here between this charge distribution from the field itself. And of course, that's because there's a plus on one side and a minus on the other. So if you rotate it, you should of course be able to tell that something happened. You can tell by looking at the field itself, or you can tell by looking at the charges themselves. They kind of go together. So if there's a left-right asymmetry in the charge distribution, there's going to be a left-right asymmetry. You can tell by looking at the field that something happened behind the curtain, so to speak. Okay. So I guess the correlator to this is if upon rotation you can tell that the charge, that change occurred, you can tell by the electric field as well. So they kind of go together, okay? If there's a left-right asymmetry in the charge, there'll be a left-right asymmetry in the field, and you should be able to look at either one and tell that something happened behind the curtain. And so what this test is really for is to sort of to make some symmetry arguments as to why the field should look a certain way if you know something about the charge. Let me give you another example. Here's a double charge configuration. And so as a plus charge and a plus charge, this is what the field of a double charge looks like. I'm going to put my curtain up and I'm going to change it. And you're going to look at that. Can you see any change? Well, I can't draw very perfectly, but if I did in fact rotate it from this to this, and you can't tell because there's a plus charge on the left and the right. It's perfectly symmetric left-right. And so if I can't tell from looking at the charges, I shouldn't be able to take a look at the fields either. So you can see that the field is the same, whether you look like this or like this. However, let me do a curtain test here and tell me, I'm going to cover up the charges themselves. You tell me if you notice any difference. Okay. And of course, now you notice the difference because I have rotated it only 90 degrees, and now the charge ends up in a different place. And of course, I can tell, even if you couldn't see the charges themselves, you'd be able to tell right away, just from looking at the field, that this field is different from this field. So this particular charge configuration might have a left-right symmetry, but it's not completely symmetric in space. But now, imagine, instead of a point charge, I had a completely spherically symmetric charge, in which, by the way, it's hard to draw because essentially when I draw a point charge, I have to draw, I can't just draw a dot. Completely spherically symmetric charge distribution, you can make all the same arguments. If I rotate this in any way, okay, no matter what I do, okay, you won't be able to tell that the charge is any different. It's a perfectly spherically charged distribution, and I can't tell from looking at the, if I can't tell from looking at the charge itself that any change occurred, I shouldn't be able to look tell by looking at the electric field either, okay? And so what that then functionally means, and this is a big realization, is that if you do have a spherical symmetry, okay, and what I mean by spherical symmetry, for those of you that have seen this in math, if my charge distribution, my charge density, it can generally be a function of r, theta, and phi. Those are my spherical coordinates, if you haven't seen that in math class. So if you can't tell that I've rotated it this way, okay, that's theta, and phi is actually the rotation in 3D space this way, okay. Obviously, I'm drawing these on pieces of paper. I'm not working with 3D models, but if you rotate it this way and you rotate it this way, and you can't tell because the charge density does not depend on either of those things. It only depends on the radial only. Then the argument is that the electric field can actually only depend on radial distance as well. If you can't tell from rotating the charge itself because it's a function of radius only, then you can't tell by looking at the electric field either. And that actually must mean that the electric field looks exactly like this. It is radially outward. So if you have spherical symmetry, if you're, this is where Gauss's law really shines, one of the cases where it really shines. If you have that your charge distribution is spherical, it is a function, the charge density is a function only of radius at best, but not on left, right, not up, down, but just a function of radius. How far out is this charge distribution or something? And you shouldn't, by radial symmetric, I mean, no matter which direction you go out, you should have the same experience, okay? You should see the same charge density only. It should not depend on where you are this way, where you are this way. It only should depend on radius at best, okay? If it's a function of radius only, then you can make a argument that the electric field should only be a function of radius. It'll be radially outward only. And that is a major, major shortcut. And in fact, what that allows us to do is to jump right in and solve not just the point charge, but any spherical symmetry, as long as it's not, you know, we can't do stuff like this where it's a sphere and it has more charge on the plus side, one side and the other. We can't do that. That doesn't have radial symmetry, but we could do stuff like this. The charge is all on the surface evenly. We could do that. Okay, that has radial symmetry. There's no charge, and then there's charge on the surface, but every single time you go out from the middle, you'll have the same experience. That's radial symmetry. We could do that, and we will do that. We could have that the charge is uniformly distributed. okay? But again, if we go out in all directions and we have exactly the same experience, that's radially symmetric, we can solve that. We can even do, and I'll show you how to do this, it could even be that maybe there's a lot of charge in the middle, like this, and then there's less charge on the edge. Okay, we can even do stuff like that. But as long as you have exactly the same experience and you see the same charge distribution going this way versus this way versus this way versus this way, we can do that. Okay, so we're going to do all of these cases as long as the charge distribution is radially symmetric. Then the electric field will be radial only. Okay, so not this one, because obviously there's a left-right symmetry problem here, but here, with the charge all on the surface, that is in fact what would happen if this were a conductor. The charge would live all on the surface. Excess charge lives on the surface. This would be a uniform charge density, and then this would be the charge density is not uniform, but it is a function of only R. And I'll show you how to do all these cases in this next video here coming up. Okay, so first of all, before we do anything else, oh, I forgot, let's do it over here. Let's just do the point charge itself. So I'll copy this to a new piece of paper. The point charge itself, if the field is completely radially symmetric, we use Gauss's law. Okay, so first of all, remember that this is always true, but this part requires a high degree of symmetry, and so we want to place a Gaussian surface here that will make the relationship between the electric field and the surface easy. And in this case, your Gaussian surface is going to be, in this symmetry, is always going to be your Gaussian surface will be a spherical shell. So your area is going to be a spherical shell. And we have to put it somewhere, so we put our testing surface. Remember, this surface is only a means to an end to get from the charge to the field. So I'll just put it at a distance lowercase r. Okay. So first of all, let's get started. The enclosed charge, pretty easy here. That's just that point charge right there. That's it. If this is plus q, that's inside. And then, if you look, the directions of the normals here. Of course, the whole point of putting the Gaussian surface like this with the charge right in the middle is that then these normals are all 0 degrees to the field, and we don't need all this integration business. This is just E dot dA. In fact, it's even just EA cosine of 0. So what we have here is EA is equal to, from this side, this is plus EA is equal to plus Q over epsilon naught. What is the area of a spherical shell? The area of a spherical shell is 4 pi r squared. And so we throw that in there. And let's see what we get. The electric field strength is going to be Q epsilon naught over A, which is Q over epsilon naught 4 pi r squared. This would be a good moment maybe to point out that 4 pi epsilon naught in the denominator is actually K. And so this is KQ over R squared, which of course is your classic formula for the point charge. We've just reinvented the wheel here, or more accurately, we have shown that the information contained in Gauss's law is exactly equivalent to that of Coulomb's law. And so I mentioned at some point along the way here, I would show you that Coulomb's law is indeed exactly in agreement with Gauss's law. Okay, so there it is. Okay. Now, a couple things I want to point out. The property of the Gaussian surface is in here. R is the radius of your Gaussian surface, and in the last video, I made a big stink about the lowercase a, the end caps of your Gaussian box had to get out of the way, get out of there, because the property of the Gaussian surface that is just your testing surface should not be in your final answer. The reason why R is okay here is because even once you take away your Gaussian testing surface, R does have some meaning in the picture beyond that. And of course, it's just how far are you away from the point charge, okay? So sort of the corollary is that if the properties of your Gaussian surface have physical meaning even if the surface is removed. Remember, the surface is just a tool that you have to get rid of once you're done. Where you don't want hammers and saws laying around on the floor of a new house. But if the properties of the Gaussian surface do have physical meaning, even if the surface is removed, they are okay. Okay, you can leave them in there, okay? So I'll show you where in the notes last time they had to get out of there. So A here in your infinite plane example, the end caps, if you take away the Gaussian surface, A has no meaning for an infinite plane. But here, certainly, even after you take away the Gaussian surface, R is just how far away from the point charge are you asking about the field, okay? So that right there, that's your point charge. Is of course nice to see finally that the point charge formula does pop out of there, and you can kind of convince yourself that if this weren't here, then of course that would not actually occur. That's important here. For this to give back Coulomb's law. Okay, so that right there is the point charge. And let me remind you, of course, that the electric field strength of a point charge, the graph looks something like this. It's kq over r squared. And the voltage, of course, we have also talked about the voltage is kq over r, okay? That should be old news. But I'm going to put those there for reference because we're going to compare some other stuff to them in a moment. So let's go ahead and look at, instead, I'm going to have a, I guess this is technically my second example because I did the point charge, but let's call it my first proper example here. My first example is I'm going to have a conducting sphere with total charge Q. And my question is going to be, what does the electric field and voltage look like both inside and outside? Okay, so let's go ahead and draw this. And I guess I should say that it's a conducting sphere with total outer radius r. I'll call that capital R. So let me draw it here. This is all material. Okay, this is all conducting material, but as we learned, the total charge on a conducting sphere is all going to live on the exterior. Okay, so that's plus Q. And so let's go ahead and work on this. Now, this does have complete radial symmetry. So this does have all the symmetry requirements. We talked about that. And so what that means is that the electric field, if it exists at all, must be radial, okay? And again, if it wasn't radial, okay, if it was something more complicated, then we would be able to see some asymmetry in the electric field, even though we'd see no asymmetry in the charge. So it would be weird in that curtain test. If we covered this up, we could rotate this. We would not see any difference in the charge itself, but we would see an electric field that's somehow different, and that can't be, okay? We need to be able, if we see some shifting in the electric field, we need to see some shifting in the charge as well. Okay, so let's go ahead and work on the outside part first. Okay, now we have just argued that the electric field of this is completely radial, and that's going to greatly assist us. In fact, we're going to go ahead and be able to drop in the exact same Gaussian surface. That Gaussian surface, again, I'll reserve little r for that. However, the charge itself all lives on a conducting sphere that is of radius little r. So right now we are outside. That is to say, we are interested in, what is going on outside the confines of the shell. And let's go ahead and work it out. I'm just going to go ahead and skip to the chase. All the same arguments apply here. I'm just going to skip to this part right here. EA equals Q over epsilon naught. And again, if I've centered the, if I've put out my Gaussian surface here, it's a spherical catcher, it's 4 pi r squared. That is always what you put in, okay? When we're working in the spherical symmetry, the A is always 4 pi little r squared, okay? That is always the case. You can count on that, okay? How much charge is enclosed? Well, we're outside, so all of it, right? Since we've managed to put all of it, I'll just go ahead and put it plus Q. And before I go too far, I want to point out that there is not a lick of difference in this calculation versus this one, okay? I'm going to get the same answer, okay? I'm going to eventually get E equals KQ over R squared, and I'm done, okay? Now, this is a remarkable fact, is that the moment you get outside of this thing, it does not matter whether or not it is actually a conducting sphere with Q all on the outside, or if it's exactly a point charge, okay? So this, I like to say, quote unquote, collapses immediately onto this, okay? So the moment you're out here, the moment your Gaussian surface is outside, okay, the electric field that you are seeing is identical, indistinguishable from that of an equivalent point charge, okay? So it's like this whole sphere just went and just collapsed into there. The field that you are seeing is no different, okay? So in this spherical geometry, okay, when you are outside, the field collapses right onto a point charge formula immediately. Now, I say immediately because, of course, back in homework 2, we talked about when you zoom super far out, eventually the field will join up with KQ over R squared. I'm not saying not just necessarily only far away. I'm saying the moment you get outside of this, the field is indistinguishable from a point charge, okay? So I'm not talking about earlier when, you know, you got really far away, and then eventually some whatever, like for instance, the ring of charge or something like that. You had some crazy hold on, that's not quite correct. It might start off like this, but then eventually it'll join up, okay? I'm talking about immediately, okay? So what I'm talking about, if I'm sketching the electric field here, radial component, or the magnitude of the electric field versus R, the moment you get outside, okay, the electric field will be exactly the same of the equivalent point charge. So if the equivalent point charge is red, okay, it looks like this. So the point charge, obviously inside is a different story, but the moment you get outside, the field looks exactly the same as the equivalent point charge, okay? So that's a really important thing about whenever you have the spherical symmetry, you are safe in knowing that the moment you get outside and you enclose all the charge, the field will collapse immediately to the equivalent point charge. And the Q, of course, is the Q on the whole thing. So that's the field inside. Let's talk, or outside, let's talk about inside. In other words, where some value inside. Well now, if the field, if it must be radial, we can still use EA, Q enclosed over epsilon naught, okay? So if there is a field in here, it's gotta be radial, okay? Otherwise there would be some asymmetry in the field that I could tell, and there can't be because there's no asymmetry in the charge. So I guess I'll do this Gaussian surface in a different color just so that we can see it. So now my testing surface is inside. And what I noticed right away is that there's no enclosed charge. Remember, the charge is all on the surface. And so if the enclosed charge is zero, that only way for this equation to work is if the field is zero, and that in fact is correct. The electric field is zero, okay? Which, by the way, it is a conducting sphere, so we knew that to be the case. It had to be. There's no net electric field allowed inside a conductor, but even if this were like, say, like a, you know, there were no material in here, this was just like a, you know, like a conducting shell, like a, it was all hollow inside, it was all not conducting material, this would still hold, okay? Now we've just discovered something remarkable. In this symmetry, if the enclosed charge is zero, okay, not only does that mean is that the flux is zero, but because we have enough symmetry, that actually means that the field is zero as well, okay? So that extra bit of symmetry, that got cut off a little bit. So the enclosed charge is zero. That always means the flux is going to be zero, but with enough symmetry, we also know the field is zero. So essentially, the only way we can get zero flux here, with knowing that the field, if it exists, must be radial, is if the field itself is zero. Otherwise, it would be picked up by this Gaussian surface, okay? If there was any radial field here, okay, it would be picked up by the Gaussian surface. And if there is no enclosed charge, if there is no flux, it must be because the field is zero. Now, let me compare and contrast that with the previous examples, okay? So in my previous lecture, I mentioned that, let me do another one. Okay, let me do this one, okay? So, now let me do this one. Okay, so we had this right here, and we said, okay, there's no enclosed charge, so that must mean that the flux is zero. But that flux being zero is actually due to the fact that there is a bunch of negative flux and a bunch of positive flux that all adds up to zero, and that the charge itself, in the field itself, is not zero anywhere along this. It's just that the field is causing just as much negative flux as positive flux, and so you cannot follow that last step, okay? So the enclosed charge being zero means the flux is zero, but it does not necessarily imply the electric field is zero, and as you can note, I noted here, I said come back later. Now with that extra piece of radial symmetry, okay, and that's key here, okay, we've deduced that the field, if it exists, must be radially symmetric, so there is no way that this could be a combination of negative and positive flux that leads this to be zero. The only way for the flux to be zero is if the field itself is zero, okay? So, again, these two always follow from each other, but that extra piece of symmetry allows us to jump to the fact that the field itself is zero as well, okay? So, what do we have here? I can draw myself the electric field is zero on the inside, and then it jumps up like that. And it jumps up to immediately match that of if it had been a point charge the whole time, okay? So that's the electric field of this thing. Now let's take a look at the voltage. Now the voltage, well, we can already conclude that if the electric field outside is indistinguishable from a point charge, then the voltage must be as well, okay? So outside, which is to say we're outside the object, V is equal to KQ over R, okay? So I can make a little chart here, and then inside, what happens when we're inside? We'll come back to that one. While I'm at this, I should probably summarize my electric field results as well. So outside, my electric field is indistinguishable from that of a point charge. And inside, it is zero. Okay. All right, so let's figure out, this is, of course, the last missing piece here. What's going on with the voltage? So this is where I apply my stuff from before. I can go from the electric field to the voltage like this, and I remember I am inside. I'm trying to figure out what's going on inside, where the electric field is zero. Okay, so that zeroes this whole thing, and it tells me that the voltage change is 0. And that tells me, okay, the voltage hasn't changed from no matter once you get on the inside. What does that mean exactly? Well, if I integrate from the surface to the any value of R inside, okay, then the difference between the voltage where I end up and the voltage on the surface is 0, which means that the voltage inside is identical to that on the surface, okay? So, luckily, I have a formula for that. This is valid anywhere outside, and so I'm just going to evaluate KQ over R. So the voltage on the inside is a constant, and I can draw what that looks like. In fact, let me go ahead and draw both of these top, just so I can compare them. Here's the surface of the conductor right here. I'm just going to replicate my previous graph like this. So it goes 0 on the inside, jumps up like that. And I guess just for technicality's sake, this is the radial component, although since I use positive charge, this doesn't matter if it's the magnitude or the radial component, they're positive either way. Okay, so here we said this is 0 inside, and then outside it jumps up to identical to a point charge. Over here, the outside, okay, so this is KQ over R, just like this was KQ over R squared. And then at this moment, the voltage does not change anymore. It actually remains constant, okay? And so the value of this constant is KQ over big R squared, okay? So the moment you get inside, it doesn't change at all, okay? So let's talk about why this makes sense conceptually. If you think about what's going on here, what you have is that if a charge, let's say a test charge, let me do it in a different color. If you had a test charge that was just kind of wandering around here, and then you kind of give it a little poke, I guess, to get it moving, the entire time that it's inside, it would just coast along at a constant speed. That's because there's nothing pushing on it, okay? So inside, the electric field is 0, so the force is 0, which means that the speed of it is going to be constant, okay? So whatever little push you gave it is going to just maintain that. There's nothing to push on it. And then if you, say, put a little hole here, a little tunnel it could freely travel in, it could just jump right off the surface, okay? At this moment, it is suddenly going to experience the full force of the electric field now that it's outside, and it's going to go shoom, and it's going to get pushed off and go faster and faster and faster, okay? So it kind of just goes coasting, 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 and whoosh, right? No force here, and then suddenly all this force picks up. That force, of course, does diminish with distance, so it gets pushed hard at first and then less later on. Now, how does that make sense from an energy standpoint? Well, when you're inside, we said that the speed should be constant. Well, if the speed should be constant, well, that means, of course, that the potential energy can't change because the kinetic energy can't change. So it's just coasting, so to speak. Now, that makes sense here. If you have something over here, it might have a voltage, but there's no voltage change, right? So here, because the voltage is constant, the voltage is constant, which means the potential energy is constant, which means the kinetic energy is constant, which means the speed is constant. These are all constant, and it just kind of coasts along with whatever pre-existing speed it has, and then here it kind of drops in the half pipe, so to speak, right? So at this moment, you're going to have that the voltage decreases, so the potential energy decreases, kinetic energy increases, and it's going to go faster, okay? So it makes sense here remember that voltage itself does not give you anything. It's the voltage change, right? Changing voltage allows you to change your potential energy and allows you to increase or decrease your kinetic energy, as the case may be. But the voltage value itself, okay, that's just going to be constant, and then only when the voltage changes does it allow you to speed up, okay? So outside, all this stuff changes, okay? So that makes sense. So whatever constant value it has, that makes sure if the voltage is constant, then potential energy, kinetic energy, and speed are all going to be constant too. Now you might ask, well, why did I consider it to be this particular value? Well, the thing is could you say that it's 0? Okay, well, I didn't say it was 0. I said it does not change. You might say, can I have it be a different constant? Could I have it be like this other constant here and have it just jump up like that? Well, you wouldn't want, or maybe you could even say the voltage is 0. Well, you wouldn't want to do that because you've already set a 0, okay? V equals 0 is already set at r equals infinity. This is what I made such a big fuss about setting zeros in some of the previous videos, is because you need to be deliberate in understanding where you're setting your 0, or in the case of kq over r, it already has built into it a 0 point set. The V equals the 0 voltage is already set really far away. You can't set it twice, okay? So there's no multiple V equals 0 in the same problem. No multiple V equals 0 in the same problem. That doesn't make any sense, okay? So once you've picked the V equals 0, you want to stay with it. So it makes sense to pick it at this point because then there is no weird discontinuity in the voltage value. Having a weird discontinuity in the voltage value is a problem, okay? Let me show you why, okay? If you have a voltage graph and it has a weird jump cut, like so, whatever, okay? What that actually means is that there are, in fact, two different potential energy values simultaneously, okay? At the same R value, you have two different V values, which if you put a charge there, that's two different potential energy values at the same place, okay? That does not make sense. We don't want that, okay? So some of the requirements that we're going to put on these things is that for your voltage function, okay, you want to make sure that your voltage value is continuous, okay? In other words, you can have stuff like this, you can have stuff like this, but you cannot have a sudden jump cut like this, okay? So no jump cuts in your voltage, okay? Because that would mean that you'd have two different potential energy values available at the same R. It does not make sense, okay? So we want your V values to be continuous, and we can actually force this to happen, okay? We can make sure of this, okay? And the way that we do this is by good management, your integrations properly. Making sure pass the previous functions, previous V values onward into the next step of the problem. So what I did here, of course, is that I was working from the outside in, and this function that on the outside was already predicting a value for the voltage at the surface, and I just said, well, I'm just going to keep it at that value going inward, okay? So that made sure that there was no jump cut whatsoever in my voltage, okay? So let me go ahead and resketch these because I got them a little bit messy, but my voltage and my electric field function look like this. Like that. And I like to sort of imagine this like it's kind of like a little skateboard or something like that. If you had a little skateboarder, okay, you could imagine them kind of cruising along on the flat part above the half pipe, they'd just be coasting at constant speed. There's no opportunity for energy exchange, and then suddenly they would go whoosh, and they drop in. Voltage change allows you to, gives you the opportunity to change energy. The other thing that you might complain about is if I've just made a big fuss about the voltage value being continuous, how can I get away with having a jump cut in the electric field? Well, that's a little bit more okay because electric field doesn't tell you about energy, it tells you about force. So to me, it's okay to think of it like that you know, you have a charge that's coming in from the inside. It feels no force, and then suddenly that force turns on, right? So that force in this moment just suddenly turns on, okay? And the reason why this kind of jumps right up through the roof here is because we're essentially watching the force turn on essentially instantaneously. So that's okay to me. That's sort of more okay to me versus if you have a jump cut in your voltage, it's just basically saying that your potential energy at that same place is two different values. The more practical reason is that we can actually make sure that the voltage value is continuous. We can actually ensure that, whereas we don't really have any choice about the electric field. In some ways, this is kind of a pathological example because we go from no enclosed charge, no enclosed charge, no enclosed charge, and suddenly it's all enclosed because we, of course, distributed this charge all on the surface. This is a kind of a pathology about this particular example that we're not going to actually have any issues with in the future examples. The last thing I want to remind you is just going back to double check. We should go back and double check. We know that just when we integrate voltage or integrate electric field, we can get voltage. So we should double check that going back the other way, it makes sense. And in particular, this tells us that the electric field is the negative slope of the V versus R graph. So let's double check here. The slope here is 0. The value isn't 0, but the slope is 0. Okay, so that tells us that the electric field is 0. Okay, well, that checks out. It is 0. Okay, then the electric field, we'll come back to this kink here in a minute. This kink here, of course, anytime you have a kink, you have that the slope is undefined. Slope is undefined. And if that's the case, well, it is kind of undefined. That's kind of what the heck is going on here. It's jumping up, right? But then the kink, I guess I said I come back, but I just talked about it. Then the electric field jumps to its, the slope jumps to its maximum value. And of course, that's the slope is negative max, which tells us the electric field jumps up to its positive max, which, by the way, is kq over big R squared. And then the slope, still negative, gets smaller and smaller, and that of course tells us over here that the electric field is positive, getting smaller and smaller. So you can see here, this is a kind of a good way to double check, right? Once you've generated the voltage from the electric field, then you can double check that the negative slope of this is equal to, gives you back this. So the negative slope of this graph gives you back this graph. Now these kinks are annoying, but again, for the voltage function, we can force the value to be continuous. And as a second bullet point, which I guess I should add here, sorry, this isn't order, but ideally, and again, this is not always possible, the voltage function should be differentiable as well. And differentiable, of course, means a defined slope, okay? So that means it can look like this, but we prefer it not to look like this if possible, right? With this weird kinks that don't have any slope. Now, in this case, we couldn't avoid it, but if the voltage is differentiable, what that means is that the electric field is defined everywhere, always. Because remember, the negative slope of that graph is the electric field. So as long as we can take the slope of the voltage, we can get the electric field. As long as taking the slope is possible, then we can, the slope negative value of the slope is the electric field, okay? So that right there, I think I'm going to do the rest in another video, but we have done most of the cases of what we talked about. So just to review, we've done the point charge, we've done Q all at the surface. The next case that I need to do is what if the charge is uniformly distributed, and then I will also mention what to do if the rho is a function, can't be just any function, but just of radius only. So I'll come back and tag that in the next video.